Okay, this is just a continuation of chapter 22. Here I'm going to introduce electric field. The symbol of electric field is E. It's a vector. So in order to have some information about the electric field, let's consider we have a charge, Q. This charge, let me call it source charge. Source charge. And another small charge, Q naught, let's call it test charge. Test charge. I don't know why it does this line. Test charge. Okay. So what will happen to the test charge because there is this big charge next to it? Well, if I assume I have the test charge, that means there would be a force affecting on Q naught by the big Q. And that force will be to the right direction. So there would be a force in this direction. Okay. That force is related to the magnitude of Q naught, magnitude of Q, and the distance between these two charges. So we have discussed this. So the force will be equal to K Q, magnitude of Q naught. I don't have to put the absolute value. We know now. Divided by R squared, and there is a unit vector R hat. In this case, we could say it's I hat, a unit vector I, but let's just call it R hat. Okay. So what will happen if I divide this force by Q naught? I'm going to explain why I do that. By Q naught. So when you divide this by Q naught, of course Q naught will cancel out. So you'll have something like this, K. Let's just put the magnitude. Q divided by R squared and R hat. Okay, look at this. Q was a source charge. I just named it source charge, but I'm going to explain why I named that and why I named the other one test charge. Actually, this is definition of the electric field. So E is equal to F divided by Q naught. So now I'm going to start with the definition of electric field. So I could simply say the electric field due to this charge at this location is equal to the force that affecting on a test charge at that location divided by the value of the test charge. Okay. Now the question is, if you remove the test charge, do you think the electric field will still be there? The answer is yes. Electric field has nothing to do with to the test charge. Electric field is there because we have this charge here. Okay, so this charge simply create an electric field around it. So electric field at this point is equal to that. Electric field at this point here is equal to similar equation. F is equal to Q naught. So imagine you put the Q naught here. The force will be that direction, the electric field will be that direction. So something maybe I should mention here. The direction of electric field is with the direction of the force. Of course, here I assume that our test charge is equal to positive 1 coulomb. Okay. Actually, by definition, we define test charge to be equal to positive 1 coulomb. Positive 1 coulomb, just by definition, by notation. Okay. So, if you have a charge now, Q, that means that the electric field is going to go away from it. In 2 dimensions, I could draw it that way, or the way you see it. In 3 dimensions, it's going to be like, like a sphere, and electric field line comes out from it. Of course, these lines, they are imaginary lines, but we know this is simply electric field. Just simply refer to the electric field. The question is why they are going away from it. The reason is because we define test charge to be positive. So for example, if you put a test charge here, that test charge will move into that direction. If you put it here, it will move that direction. If you put it here, it will move that direction, and so on. Assuming that source charge is positive. The question is, what if the source charge was negative? Well, if we have a negative charge, the electric field will be toward it. The reason is because if you put a test charge at any location around this negative charge, okay, that test charge will go toward the negative source charge. So if I put a test charge here, Q0, because Q0 is positive and because this charge is negative, of course there will be a force that try to bring the test charge close to the negative charge. There's another question might actually come up. What about the test charge itself? Does it have an electric field? Of course the answer is yes, but the way we choose test charge is a small charge in a way that electric field around it is very small, does not change the electric field of the source charge. To summarize this, electric field is always available whenever there is a charge, okay? And the electric field lines simply refer to the direction of the force that will affect on a test charge located at that location. That's one thing. Second, the electric field is there whether you have a test charge or you don't have a test charge. Actually, I use the test charge just as a tool to detect the electric field. Think about the screwdriver. You use it to open a screw and then you throw it away. It's just a tool. Okay? So the screw is there. The screwdriver will simply use it to detect it or to open it or to tighten the screw. Okay? So this is similar. So in a summary, electric field definition, E is equal to force affecting on a test charge located at that location divided by the value of the test charge. So is equal to K Q divided by R squared and then some unit vector R hat. It's important to also know that this Q is not the value of the test charge. This is the value of the source charge. Cool? Okay, so electric field is a vector. So we have to deal with it like similar way we dealt with, forces. If you have two electric field in a location, in one point, you have to add them vectorially. When I say vectorially, it means you have to deal with them like vectors. You find their components, you add all the x component together, you find all the y's component together, and then you deal with them the same way we solve questions in forces. So let's go deep into this. So my next slide simply just what I just covered here. Okay. My next and second slide is just simply what I covered here. So that's the definition of our force. I get to this point. Now here I'm trying to say if you have multiple electric field, you simply add them. So it's better for me to maybe explain this equation by a problem, by an example. Okay, so I'm going to go through a few examples. Maybe my first example does not include two electric fields, but maybe my second example has 2 or 3 electric fields. I'm going to deal with it. So my first example is, again, don't worry, the solution is it's already posted in my next slide, but I want to present it this way because I want to go through it in detail. Before I do this example, just to remind you again, if you have electric field this direction, for example, that means if you put a test charge here, the test charge will move this way because the test charge by definition is positive. So the direction of the electric field is the same direction of the positive charge located there. Okay? Which means if you put a negative charge, it will go opposite to the electric field. Remember that. Okay. Here the question is about a suspended water droplet. A water droplet of mass, so we have the mass of a water droplet, is located near the air, near the ground during a stormy day. An atmospheric electric field of magnitude 6, 10 to the power minus 3 Newton divided by Coulomb. I forgot to tell you the unit of electric field. Electric field is equal to electric force divided by Q0. So the unit of it is obvious. has to be equal to Newton divided by Coulomb. So that's why we have a unit of Newton divided by Coulomb. And the question says this electric field is points vertically downward. So this is electric field downward. So I just explained, and this is the ground. Because electric field downward, if there is a charge, positive charge, somewhere here, that charge will move with the electric field. If that charge was negative, it will go upward. Remember that. Okay. Now, in the vicinity of the water droplet, so it means that we have the water droplet located somewhere here. So let's say this is water droplet. Okay. So it's located there. So what happens to this water droplet? The droplet remains suspended, meaning does not move upward or downward. So what's the electric charge on the droplet? The question looks like easy, and it looks like implies some kind of equilibrium, because the question says something is suspended there. Well, if you are the droplet, you know there is a force on you, which is mg. If there is no other force, of course you're going to go down. The droplet will go down, right? So there must be another force upward. So what's that force? What's this line? Let me erase this. I don't know why sometimes this line comes. Eraser. Okay. Again, go here. Pointer option, pen. So there has to be a force. What's that force? Well, it has to be electric force. But let's go back to this. The droplet must be negative charge. Why? Because only negative charge has a force opposite to the electric field. Makes sense, right? Because if the water droplet was positive, it will go even faster downward. And because it's suspended, so we know, let's assume upward is y axis. So summation of Fy has to be equal to 0, which means F electric force has to be equal to mg. That simply tells me, but electric force is equal to what? Force is equal to QE, according to the equation. I am only interested about the magnitude, so is equal to Q multiplied by E. This electric force is equal to mg. And the question asks us for the charge, so Q is equal to mg divided by E. And I have all the information, so we could solve this. 10 to the power minus 12 kilogram multiplied by 9.8 meter per second square. This is acceleration due to gravity, and we have E is equal to 10 to the power what? Power 3, I guess. Newton divided by Coulomb. So Q, you're going to get some values in Coulomb. Now it's important, this is only going to give you the value. This is magnitude. It doesn't tell us if it's negative or positive, but our thinking, we already knew the charge has to be negative. Because if the charge was positive, this force will be downward. You will have something like this. You will have mg and you will have Fe. So it will never be suspended. It will actually go much faster and hit the ground. Let's get into some other questions. Before we do a question about electric field or finding electric field at a point, I have a few hints that is going to help us to do that. So if the question was asking to find electric field at a point, it's a good idea to follow the following steps. For example, first one is to find electric field at a point, do the following. A, assume there is a test charge at that point. Of course, the question might not have any test charge. We just assume there is a test charge at that point. So after that, we're going to find the direction of the electric forces. If there is a test charge at that point, there will be forces affecting on it if there are charges around it. Okay, and of course, the direction of the electric force will be the direction of the electric field. Okay, so this is point 3. So what are we going to have now? We will have maybe 1, maybe 2, maybe more electric field vectors. So we will deal with them like vectors, the same way we deal with multiple forces. So let me demonstrate this with a question. But before that, again, let me just remind you one more time. If there is a positive charge, electric field is going away from it, okay? And I explained why this is the case. Electric field will be away from it, always getting away from it. If the charge was, so this is positive charge. If the charge is negative, the electric field is going toward it. So again, why is that? We explained it, but because if you put a test charge somewhere here, remember test charge is positive, that test charge will move this way. If you put it here, the test charge will move that way. But in this case, in the negative case, if you put a test charge here, the test charge is positive, so it will be experienced by a force that moves toward the actual charge. Okay, so it's going to go like this. Okay, so let me demonstrate this with a question. The solution is here, but I'm going to go through. So this is just repetition of the hints of the steps that I talked about it here. We're going to apply here. And after you solve 1, 2 questions, there is actually a quicker way to get into the electric fields vectors. So here we have electric field due to 2 charges. Now we have 2 charges, Q1 and Q2. So let's read it. Charges Q1 and Q2 are located on the x-axis at distances A and B, respectively. So this is A, it's mentioned here, B is mentioned here, and this is the origin. Okay, from the origin, as shown in this figure. So the question asks A, find the components of the question only asks for the components. Find the component of the net mean total electric field at point P. So it's that point, okay, which is located at position 0, y, means x is 0 and y is equal to y. Notice in this question there are no numbers, so we have to deal with it numerically. This kind of questions, you have dealt with it in previous physics course, maybe other courses. The way we approach it is, we assume we have Q1 because it's given, we assume Q2, we just think about like a number. We assume we have Y, we assume we have B, and we assume we have these two. Okay. But of course, we don't know what are the components of the net force. This is something we have to do it. So first step is, let's do all these steps. So first step is, we need to know what are the direction of the electric fields at point P. So just assume there is a test charge located at point P. So what's going to happen to that test charge? Well, that test charge will be pushed away because this one is positive. So the electric field produced by Q1 at the location of P will be into that direction. This is E1. The E1 is the electric field produced by Q1 at point P. Okay. What about Q2? Well, Q2 has electric field. Remember in the previous slide we said if you have a negative charge, electric field always goes toward it. So electric field produced by Q2 at the location of point P, is going to be equal to this vector. So now you have 2 vectors. You have to deal with those 2 vectors. Okay. So the first vector is E1. So what's E1? Well, E1 is equal to K Q1 divided by R1 squared. This is by definition, right? We know the Q1 is the source charge, and we know this is when we say source charge, is the charge that produces electric field somewhere. This is also a source charge. So this is equal to Q1 divided by A2 plus A2. Why we put A2 plus Y2? Because we need to know the distance between Q1 and P, which is R1. So we need to know that distance. Simple. This is Y. This is A. So R1 has to be equal to A1 plus Y1 under square root. But here R squared. What about I2? Similarly, I2 is equal to K Q2 divided by R2 squared. Well, we have R2. Okay, we could find R2 is equal to square root B squared plus Y squared. But we need to square it, so it's going to be equal to B squared plus Y squared. Now the task is we need to find their components. So in order to find their components, you need angles. So for example, this angle theta, oops, sorry, this angle theta is the same angle given here. How do I know that? Well, think about this line. If this is theta, this is going to be theta, right? So this is theta, this is theta. What about phi? Well, if this is phi, this is going to be phi. Now I can write E1 in terms of components. But let me remind you something in physics 1. Do you remember this? A vector can be written as AXI plus AYJ. I'm going to do it for these two vectors, okay? So E1 is equal to E1x, this is E1x, multiplied by I, plus E1y, this is E1y, multiplied by j. This is when I should write this, where I could write this here. This is E1x multiplied by I. I just used something that we know from physics 1, which is unit vector notation. So repeat the same thing for E2. So for E2, E2x, it's simply this, cosine involved. E2y is simply this. Now you better know why I put negative here, right? Why there is a negative sign here? Because E2 has two components, one to the positive x, but one to the negative y, right? But E1, so this is E2x, this is E2y. That's why there is a negative sign here. So the next task is, before I go to the next task, let me say this is E2x, and this one is E2y. So the next task is, what's EX? What's total EX? Simply is E1x plus E2x. Means this term plus this term. And that's what we're going to do here. What about total EY? Well, is equal to E1y, E2y. Okay? Which means this term plus that term. And that's what we're going to do it here. That's done. That's what the question asks for. Just find the question just say find the components. But it looks like the question has other parts. I'm going to do maybe one more part, and the other part maybe you could go through it. So the second part says evaluate the electric field at point P in the special case when Q1 is equal to Q2. That's easy. And A is equal to B. So what are we going to do here? Instead of every Q2, just change this Q2 to Q1. Change this into Q1. Just name it Q1. And change every B to A. So change this B to A. Change this B to A. Then maybe a little bit make it nicer. Find any factors between them. So for example, the top equation here, you could take out, okay, sorry, here you could take out Q. If this is Q1 and this is Q1, you could take out Q1 outside. If this is A2 plus Y2 and this is A2 plus Y2, you could take this component outside and factorize them in, and you could make it nicer. Okay. Now, I just promised that I'm not going to do, or I just said I'm not going to do C, but let me just give you one example, one info, because you might not don't know that. Find the electric field due to the electric dipole. By the way, this is called electric dipole. Why? Dipole means two. Any electric dipole simply consists of two charges with equal magnitude and opposite direction, opposite sign, I should say. Okay. So after you find the answer of B, C will come. So C depends on your answer of B. Find the electric field due to electric dipole when point P is at a distance y is much larger than A. Remember, if y is much larger than A, okay, means you could actually ignore A with respect to y. For example, if y is 2 meters and A is, say, 10 centimeters, you could ignore 10 centimeters as a comparison to 2 meters. That's what the question. So you could simplify your answer. Okay. Okay. I think we're done with the definition of electric field. This is just a note that is going to be clear when I'm going to talk about the next chapter. So just one final note. This equation that we deal with it for finding electric field, this is, by the way, only correct for point charge, because in the next chapter, we are going to deal with distribution of charge. What I mean by this is we're going to deal with, for example, a disk that has distribution of charge, maybe a rod, maybe a cylinder. These are not point charge, so this equation cannot be applied there. Over there, when we deal with the actual object, we need to use integration. Basically, we make these objects into many small pieces, and then we do integration. But that's something that we're going to do in the next slide. But I made it sure to write it here because it's a very common mistake by some student. Some students always tend to use that equation, the above equation, for every single case. That's not true. This is only true correct for point charges. If the question has extended objects such as rod, cylinder, disk, we need to use integration. We're going to talk about this next chapter. My next few slides simply talk about something that I have already mentioned it, which is electric field lines, right? If you remember, I talked about this. If you have a positive charge, electric field lines goes away from it. So the first thing you need to know is, these electric field lines, they are not real. You don't see them. If you have a charge, let's say a negative rubber on a table, okay, you put a negative rubber rod on a table, or positive glass rod sitting on a table. You don't see lines surrounding it. They are just tools for us to study electric fields. So first thing, they are not real. They are not physical, real objects. They are just imaginary lines. Second, the more lines you have means the more the higher electric field you have. So, for example, in this picture, these electric field lines, these are simply, we call them electric field lines. Here we see they are closer to each other. Means electric field here is larger. Here I see they are far from each other. So electric field here, I'm going to just write a smaller. Okay, and so on. The second thing is they are all parallel. They don't hit each other. They are all parallel to each other. They don't hit each other. Okay. So the number of electric field lines just related to how strong electric field is. This is something maybe I'm going to just go through it very quickly because you know that. This is positive charge, electric field lines is going away from it. This is negative charge, electric field lines is going toward it. You know why? Because if you put test charge next to them or anywhere, they will go with the direction of the arrows, What if you have two charges next to each other, like a dipole, the one we just mentioned in the solution? Well, in that case, electric field lines will emerge from positive and will go into the negative. Okay. So one way to think about it is, what happens if I put a test charge here? Just think about it, a test charge. If you put a test charge here, remember test charge is positive. So what's going to happen to it? Well, this negative charge will try to pull it toward it. So there would be a force this way. But this one also tried to push it, so it's going to be equal two forces. That's why the electric field lines in the middle going toward the right. What about here? Well, this one try to push it kind of this direction, electric field, but the electric field of the negative goes here, right? So the total electric field will be tangent to this curve. That's why the drawing is drawn that way. In this particular case dipole, if you count the number of lines, so this is 1, 2, 3, 4, 5, 6, 7, just count all this. Let's say you have 20 lines coming out from the positive. All 20 lines will go to the negative. Why? Because their magnitudes are equal. So this is Q1 is equal to Q2. Their magnitudes are equal. What if their magnitudes were not equal? So I'm going to do this and then I'm going to go back to the other slide. Here you see this charge is bigger than this charge. So you see 1, 2, 3, 4, 5, 6, 7, I just made it up, let's say 12. So 12 lines coming out from this charge, but only 6 goes into this because this is twice as big as that. Okay. Now I'll go back to my previous slide. Remember, these two guys, these two charges are positive. So lines always going away. So look at the arrow, always goes away from it. But point C is interesting. Point C. There are no lines of electric field. Looks like electric field here is 0. We could prove it, right? What if you put a positive charge here? So what's going to happen? And let's call this one 1. Let's call this one 2. So what's going to happen to Q for test charge? Well, Q1 will push it that direction. So this will be E1. Q2 will push it the other way. This will be E2. So what will be the total E in C? So total E at point C simply is equal to 0. That's why nothing was drawn over there. Okay. What about point here? Well, let's just play with it. So this is Q0. If the test charge was located here, the electric field due to the Q1 will be that direction. With the other one will be that direction. Sorry, I did a mistake. Let me, how I can erase this? Again, go back, pointer options, pen. So the electric field from the Q2 will be that way. So it's like letter V, right? E. What's the total electric field? Well, this one has two components, right and up. This one has two components, left and up. Because this charge is equal to this charge, this component will cancel that component. So what will be the total component? Total electric field will be upward. That's why they draw it upward. So you could now say, what about this point? What about this point? And so on. Okay. Okay, so rules for drawing. We just, while I was explaining this, actually I went through all this, right? So I don't have to repeat it. Okay, now, what happens? Let's say you have electric field produced by two plates. For example, let's say you have a plate made of aluminum, another plate made of aluminum, and you made one of them positive, you made the other one negative. Now the question you might ask, how you do that? Well, simply, let's say you buy a battery in the market, one side is positive, one side is negative, and simply you wire it. You put a wire here, put a wire here. You just made one of them positive, one of them negative. Okay, if this is positive, electric field lines will go away from it. So in this direction is going to go up, in this direction is going to go downward. This is also negative, so electric field will go toward it. So actually electric field here will go this direction. Let's not be too worried about outside. Actually, electric field will go even this way, but let's not worry about that. So now you have electric field here. So let's ask the following question. If you put a positive charge, let's say you just bring a positive charge and you lift it, you keep, let it go here. This is positive. What do you think? Which direction is going to go away? It's gonna move. Well, remember, electric field direction has the same direction of the positive charge. So this guy will simply gonna move this direction till it hit this plate. Okay, remember that. My next example is, what if there is a charge? There is a charge. Let's say positive. And it's moving with a velocity v. And suddenly enters this region. What do you think is going to happen to it? Isn't this remind us of something in physics 1? This is projectile motion. Projectile motion. And the first example reminds us of free fall. Let's say you have a football and you just let it go. What's going to happen to the football? It's going to just simply hit the ground. Why? Because there is a force of gravity. Here, why this Q goes downward? Because there is electric field and there is electric force, because E is equal to F divided by Q. Because there is electric field, there is electric force. So in principle, we should be able to use all the equations that we learn in physics 1, such as conservation of energy, kinematics, in dealing with problems. Okay, so we should be able to use delta K plus delta U is equal to 0, or kinematic equation V is equal to V naught plus AT, delta X is equal to V naught T plus half AT square, and maybe the last equation V square V naught square plus 2A delta X, right? Okay, so let's do that. Now this is the same case, but just the plate, instead of making the plate up and down, the question just made it like left and right. So this is the positive charge. Here the battery is not shown, but I explained it how you do this kind of, how you charge the plates positive and negative. You simply, use a battery to do that. Otherwise the plate will simply lose its, or doesn't have a charge. A uniform electric field E is directed along the x-axis between the parallel plates of charge separated by a distance d, as shown in the figure. A positive point charge Q of mass m is released from rest. So you put a charge here. Okay. And you let it go. Of course, because this is positive, it's gonna follow the line of the electric field. It's gonna move this way. It's gonna move that way. At point A next to the positive plate and accelerates to point B next to the negative plate. A, find the speed of the particle at point B, means at the end here. A is here. Modeling it as a particle under constant acceleration. Let me remind you of something in physics 1. When you have constant acceleration, we do use kinematic equations, right? And that's exactly the case here. Because, and by the way, why there is a constant acceleration? Let me just explain. We know there is a constant acceleration because the only force affecting on Q is electric force. Fe is equal to E multiplied by Q, right? What about acceleration? Well, if you divide this by m, left-hand side Newton's second law simply tells us this acceleration is equal to E divided by m multiplied by Q. How do I know this is constant? Well, let's think about it. Is electric field constant? The question says yes, it's constant, uniform. Is mass constant? Yes. Is Q constant? Yes. So A is constant. Okay, now let's go back to the solution. The question asks us to find speed at the end. So maybe this is an easy option for us because there is no time given. So let me go back to see this equation, this equation, this equation. I did not use the first one because there is a time and we don't have time. I did not use the second one because also there is a time. We don't have time in the problem. So we're going to use this. Okay. So we say V final square is equal to V initial square plus 2A delta X. And our delta X simply is D. Okay, is D. Okay, we just got it. But what's A? It's already given here, but I already did it for you. This is A. So you just plug it in, you find V final, done. This is something we learned from physics 1, right? Second part, find the same thing, find the speed of the particle, but this time by modeling it as a non-isolated system in terms of energy. The question simply tells us, find it using energy method. Okay, so what's the energy method? Well, we could say one of the chapter 7 of physics 1, if you remember 7, we work kinetic energy theorem. We say work or total work, excuse me, total work affecting on the mass is equal to the change of kinetic energy. So what's the force that make work on the charge? Is the electric force, so it's equal to Fe delta X. Final kinetic energy minus initial kinetic energy. Okay. Right? So what's that force? Well, that force simply is equal to QE. Total kinetic energy is half mv squared. Initial is 0. Let's find for velocity. This is velocity or speed here. Speed. Our force, it's simply QE. Our delta X is D. So if you look at it, it's the same result as this. So it's two results, but using two different methods. But none of these methods are new for us. We just learned them in physics 121. Okay. A kinematic equations doesn't care if the force is from gravitational force, as in physics 1, or electric force in physics 2. Now, my next example will be something also I mentioned here in the projectile motion. Okay. So again, it's some skill that we learned from physics 1. Here, an electron enters the region of a uniform electric field, as shown in the figure. The initial velocity of the electron is given, electric field is given, the horizontal length of the plate is given, so L. Part A, find the acceleration of the electron while it's in the electric field. We just did that. We just did this method, electric field. So I don't want to do it again. I don't want to repeat again, I should say. So electric field simply is equal to E divided by M divided by Q. A is equal to E divided by M divided by Q. Oops. Okay. That's it. One thing I should maybe mention here. Remember this electron, right? Because this electron, we will ignore gravitational force on the electron. So you don't include mg, okay? Because this electron, we had, if you remember, I solved one problem where electric force was way larger than the gravitational force. So we will ignore it. All the elementary particle, electron, proton, others. When we deal with it, with electricity, we will ignore gravitational field. Okay? I think I mentioned here, right? Okay, B. Assuming the electron enters the field at t is equal to 0. So when electron enters, somebody just start time, and is y initial is equal to 0, means this is the origin. So the question tells us this is the origin. So this is assuming the electron enters the field at t is equal to 0. Okay, so the moment electron enters this field, time is equal to 0, and the question simply tells us the initial position is equal to 0. So this is the origin located here. I don't know why it does bring this this menu. Find the time at which it leaves the field. Well, again, this is projectile motion. That's something we learned from physics 1. So part B. So how we deal with this? Well, remember delta x is equal to v naught x t plus half ax t squared. What's ax? Is there any acceleration? Is there any force in the x-axis? The answer is no. So this equal to 0. In projectile physics 1, was there any? Of course, we ignored wind, we ignored friction, so there is no force. There is no force in the x direction in the projectile motion, so there is nothing to change the velocity. Acceleration is equal to 0. So when you apply this, you could easily find t. Now our delta x is simply L, so this is L is going to be equal to L equal to v naught x multiplied by t, so t is equal to L divided by initial velocity. Okay. Now part C, assuming the vertical position of the electron as it enters the field is equal to 0. Okay. What is its vertical position when it leaves the field? So the question simply asks us to find this y. So we are looking for delta y. So again, you remember that equation, delta y is equal to v naught y t plus half a t squared. A t squared. Now, what's our a here? In physics 1, what we used to say a is equal to minus g. Do you remember? In physics 1. But in physics 2, it's a different acceleration. It's actually this acceleration. Right? So a here is equal to, when we plug it into the equation, we gotta say minus q divided by e divided by m. Do you know why we put minus? Because we assume upward is positive and downward is negative. And because the acceleration is going downward, so it's we put a negative sign for the acceleration. Okay, so this is actually, I think this has to be positive because the positive, and a is equal to negative, so we're going to have a negative here. Okay, so this is done, but let me explain a few points here. If this electron was a proton, which way it will go? The projectile will be this way. Right? This is something we don't have in the gravitational field. In gravitational field, if you threw an apple, a laptop, or your phone, it's going to go this way, right? Always. But in electricity, we could play with it because we have negative, we have positive. Also, we could put negative upward, positive downward, or you could reverse all this. Okay. So we have more options in electricity. Okay, I think I am done with chapter 2. Please, learning from me doesn't actually doesn't give you full understanding of everything, because you gotta do practice, you gotta solve problems. Okay. Okay, so let me end this, and thank you for watching.